the first thing is, how do we use derivatives to link to the shapes of the graphs? How do we use the derivatives to link it to the shape of the graph? The first thing that we can figure out by looking at the graph is which part of the graph is increasing and which part of the graph is decreasing. It's like if you go from left to right, anytime you're going up a hill, we're talking about increasing. The y value is getting bigger and bigger and bigger. So if you go up a hill, we say that the graph is increasing. On the other hand, if you go down a hill, the y values are getting smaller and smaller and smaller. We call that decrease. Right? The y values are decreased. So this, if you look at a parabola here, this is the bottom of the valley. Before the bottom, right? Let's say this is -1. Before -1, the graph would be decreasing, and after -1, the graph would be increasing. And we have to describe that in what we call an interval, because it's not a particular point. So we have to describe that using interval notations. So we can say the graph is decreasing before x equal to -1, and the graph is increasing after the graph is bigger than -1. So intervals of decrease, interval of decrease or decreasing intervals is gonna be x less than -1. If you don't like this notation, we also have students using this notation, -infinity to -1. Both notations are accepted. So either you use this notation or you can use that notation, and both of them refers to the interval from -infinity up to -1. What about the interval of increase? Well, which part of the graph is increasing again? Well, it's -1 and up. X greater than -1, or if you use the other notation, it would be -1 to positive infinity. Okay, -1 to positive infinity. And then people ask, oh, what about if you stay right at -1? Well, -1 is that point where things are changing, right? We have a special name for that. This is what we refer to as a critical point in the graph. It's one of the important points in the graph. And in this case, because you're going down a hill and then you go up a hill, this is the lowest point of the graph. We also call this point the local minimum. And we'll spend more time on that later on. This guy is referred to as the local minimum. It's like the lowest point, right? The bottom of a valley. Now, if you have a graph, it's easy, right? You just have to compare the y values. If the y values are, as you go from left to right, gets bigger and bigger, well, then it's increasing. If the y values, as you go from left and right, it gets smaller and smaller, well, that's decreasing. So anytime you're given a graph, it's very easy because you just have to look at the graph and tell me. So you see how here you're going up a hill, right? Once you reach this point, you stop, and then you go down a hill. Once you reach this point, you stop, and then you go back up a hill again. So increasing is going to be -infinity to, again, x values, -1. And then that's 2 and up. So you can say x is less than -1, and then x is greater than 2. Or you can use the alternate notation of -infinity to -1, u or union 2 and positive infinity. Again, both ways are accepted. It's up to you how you want to write it. What about the one in the middle? Well, that's between -1 and 2. So you write -1 is less than x is less than 2. -1 to 2 is decreasing. Or if you use the other notation, then it would be -1, comma 2. Okay, so either notation are fine. It's up to you which notation you learned before and which notation you're comfortable with. I will accept both notations. Okay, so whenever you have a graph, this is a piece of cake, right? You just look at the graph and see if you're going up a hill, or you're going down a hill. That's all you have to do. But life is not always this easy. If you have a graph, everything is easy. But if you don't have a graph, like if you're given the equation, well, how do I know which part it's increasing and which part is decreasing? Well, the key comes into what we call the derivatives. Like, why are we talking about derivatives? If you are looking at a graph and you're going up a hill, the slope of tangents is going to be always positive. It's always going to be bigger than 0. Bigger than 0, you will have positive slopes, right? Whenever you have positive slopes of tangents, the graph is getting higher and higher. You are having an increasing function. On the other hand, if you have the slopes being negative values, then we say the graph is decreasing. You see how here if I draw a slope tangent, well, that's going to be a negative slope. What happened here? Well, that's going to be another negative slope. So negative slopes is going to give you a decreasing function. So basically, if you're not given a graph and you're not allowed to use the graphing calculator, which is what we're talking about here, then what you need to know is, well, which part of the graph is the derivative greater than 0, and which part of the graph is the derivative less than 0. And what we need to do is we need to do something called a Sine diagram. All right, so something you should have learned in the advanced function class, but obviously I'm going to talk about it again, make sure everybody understands what's going on. 3 simple steps. Step number 1, find y prime. And then, so well, actually, let's do this first. What's the derivative function here? Y prime is equal to 3x squared plus 6x, right? 3x squared, 6x. That's a 0. I don't have to worry about it. Step number 2, solve, right? Set it equal to 0 and solve. So 3x squared plus 6x is going to equal to 0. 3x, common factor out the 3x. I'm going to get x equal to 0 and x equals to -2. So there are 2 zeros. Those are referred to as critical points. They're important points. That's going to give us important information about the graph. Third step, Sine diagram. Now, I don't know how many of you know how to do Sine diagrams or you remember from the advanced function class. It's actually quite simple. You first of all plot a number line. Right? Draw a number line, and you label the x-axis, and so the x-intercepts, right? The zeros that you calculated here. So which I have a -2 and I have a 0. What happens is you have divided the number line into 3 regions. Region number 1, region number 2, region number 3. The first region is x is less than -2. The second region is between -2 and 0. And the third region is x bigger than 0. Then you copy down what the derivative function is, factor by factor. So 3x is one factor, x plus 2 is another factor, and you put it on the side. So 3x times x plus 2 is the derivative. So I'm just going to put those two on the side. Then I need to test each of the regions. I have one region here. I have one region there. And the final region over here. And I'm going to check by putting a number within each of those regions into those two factors to see if it's positive or negative. So if I want to pick a number that's smaller than -2, it can be anything. You can put -3, -2.1. I like easy numbers, so let's say -10. Well, and I don't really need to know what the answer is. All I need to know is whether this is a positive number or negative number. 3 times -10, well, -30, that's negative. -10 plus 2, well, that's -8, that's going to be negative. Negative times negative means the derivative is going to be positive. A negative times negative is positive. Now I pick a number between -2 and 0. I'm going to pick -1. That's going to be negative because -1 times 3 is -3. -1 plus 2, though, is going to give me a positive number. A negative multiplied by a positive is going to give me negative. What about a number bigger than 0? Let's not pick something hard. Let's just pick 1. 3 times 1 is 3, positive. 1 plus 2 is 3, is positive. A positive times a positive is positive. So what does that mean? I have those two regions where the derivative is positive, and I have this region where the derivative is negative. Whenever you have a derivative being positive, that tells me the graph is increasing here and decreasing over there. Anytime the derivative is positive, the function is increasing. Anytime the derivative is negative, the function is decreasing. And I have the answer right here on my sine diagram. Which part of the graph is increasing? Region number 1 and region number 3. What's region number 1 and region number 3? X less than -2 and x greater than 0. So increasing over x less than -2, x greater than 0. Decreasing over which interval? Well, decreasing is the one in the middle, is region number 2, is between -2 and 0. So over -2 and 0. Okay, that's it. So let me go back up 3 steps. Anytime you're given a function and asked to decide where the graph is increasing and the graph is decreasing, what you do is you take the derivative, right? You always need to look at the derivative. You need to look at the slope of tangents and see if it's getting bigger or smaller. Once you get the derivative function, you're going to set it equal to 0 and solve. Find the two, what we call critical points. It can be 1 critical point. It can have no critical point. You can have 3, depending on the function. So in this case, we have 2. Once we get our critical points, then we plot our sine diagram. Draw a number line and put those 2 dots there. If there are 2 dots, then you have 3 regions. If you only have 1 single dot, well, then there's 2 regions before and after it, right? So depending on how many critical points, you're going to have, different number of regions that you need to worry about. Once you have the 3 regions in this case, then you write down the derivative function, the last step. So 3x times x plus 2. And you put each of those factors on the side. And you check with a number in each of those 3 regions to see if those are positive or negative. With the sine diagrams, you can decide whether the derivative is positive or negative. If the derivative is positive, the graph is increasing. If the derivative is negative, the graph is decreasing. Okay, let me try one more and make it a harder function. Now we have a rational function, so it's a bit more work. Same 3 steps. Step number 1, which is a little harder, but steps does not change. First step, what we do is that we need to find y prime. And I hope you recognize this is u divided by v. So I need to apply quotient rule. We've been doing this for a while, so I'm not going to write out all the detailed steps. So y prime is equal to bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by bottom square. Now I need to set this equal to 0, right? So the best thing to do obviously would be to simplify the numerator, or else it's going to be a little difficult. So set equal to 0 and solve. So the denominator doesn't matter, because if this is going to equal to 0, the denominator is going to be bring to the other side, multiply 0 multiplied by anything, it's just 0. So really all I have to worry about is the numerator. The numerator is x squared plus 1 minus 2x squared, right? X squared plus 1 minus 2x squared. So now that I don't have to worry about the denominator, because I'm taking this denominator, bring it to the other side, multiply 0 by anything, it's just 0. So the numerator becomes negative x squared plus 1 equals 0. Or 1 equal x squared. That means x equal plus minus 1. Okay, so we got the 2 critical numbers. Now, anytime you have a rational function, which is what we have in this case, there's one thing you have to be careful about. What happened to negative 2x squared? Where? Here? X squared minus 2x squared becomes negative x squared. I combined them. Like terms. Those two are like terms. You have an apple, you need 2 apples, you don't have enough, you owe someone an apple. Okay, so step number 3, we're going to do our sine diagram. And we plot in our critical numbers, which is negative 1 and 1. But there is a trick to this question. Pay special attention to rational functions, which is what we have in this case. We have to include the vertical asymptote in the sine diagram, because there's a vertical asymptote in there which causes a break in the graph. Remember, the graph is not continuous. If there's a vertical asymptote, that's the infinite discontinuity, right? So you can't just say, oh, between negative 1 to 1, for example, if there is an asymptote here, then I need to consider what happened before the asymptote and what happened after the asymptote. Where is the asymptote in this case? Good news. Can x squared plus 1 ever equal to 0? Well, no solution. So there is no vertical asymptote in this case. So I don't have to worry about it, right? So if there's a vertical asymptote, we do have to include it in the sine diagram. And that's usually the most common mistake. Okay, so in this case, since there is no vertical asymptote to worry about, we have this little part, the middle part, and greater than 1, 1, 2, 3 regions. What's the derivative function? The derivative function is not just this little part, right? The derivative function is this whole thing. So don't forget that you actually have to include this whole thing in the sine diagram. Now, the numerator is just 1 minus x squared. So you can just write 1 minus x squared. But the other bracket, it's x squared plus 1 squared, right? And you keep it there. So those are the 2 things you need to worry about, right? If you want to draw the lines, you can draw the lines. A lot of times I don't even draw the lines. Right? it's not necessary as long as it's legible, it's clear in terms of what you're doing. You don't actually, I don't make my students to draw the lines, but as I'm teaching, I am going to draw the lines so that's easier for you to see, especially if you have not done this last year or you did not do a very good job of this last year. Okay. Some people say, well, I don't need to write this part, and they're right, but I'm not sure if you can see that or not. So I am going to include it in this example. The reason being, you have an x square, and then you have a whole bracket square. So it really doesn't matter what value of x you put. This whole thing is always going to be positive, right? It doesn't matter what number you put here. When you square, it's always going to be positive. +1 is always going to be positive. Square again, it's always going to be positive. So I really don't need to check this bottom part, right? But I like to include it here so that you know I'm not ignoring it, right? Because there are other times where it will change the sign. So you can't just ignore the denominator. You always have to include it. It's just in this case, it's always going to be positive. Okay. A number less than -1. Well, again, -10. -10 square is 100. 1 minus 100. Well, that's negative. Between -1 and 1, put in a 0. 1 minus 0. Well, that's positive. A number bigger than 1, let's put a 2. 1 minus 2 square. 1 minus 4 is -3. That's negative. So what does that mean? That means the derivative is going to be negative, positive, negative, where the original function is going to be decreasing, increasing, decreasing.